Well, most welcome to this concluding discussion of panel discussion related to the Big Bang cosmology and, well, to some extent also to religious belief or philosophical and theological questions. And we have a very eminent and interesting panel. We have Rodney Holder. You already know him from a couple of lectures here. He's Doctor of Astrophysics, and he has also a degree in theology. Bengt Gustafsson, very much welcome. You are a Professor Emeritus of Astrophysics here at Uppsala University. And Katarina Pajchel, we just heard, you are doing your postdoc in particle physics for CERN. My role, I understand, is the ignorant, simply formulating questions to you three, and I will try to take this position. It won't be difficult for me to but in order to put some interesting questions, you have to know something. But I will start with a very general question, and that is, in a way, the general topic of this conference: the relationship between science and religion. And of course, it could be related a bit to this specific area. How is it? The questions that we discuss in science, in physics, are they in some way related to theological or philosophical questions, or not? What would you spontaneously think about this relationship between science and religion? And any one of you can start.
Well, all right, thank you. I happen to think they are. It's not that theology sort of somehow interferes with science or wants to dictate to science what its findings might be or anything of that kind, or to seek a God of the gaps type of answer to questions that science can't answer. So clear the ground a bit there. But I do think the science raises very interesting philosophical and metaphysical issues. And maybe some of the findings of the science point to something beyond the science itself. And so in Katarina's presentation, this whole process from these incredible particle reactions that go on in the very early universe to where we are today, that whole story is utterly remarkable and could have gone lots of different ways depending on the values of the physical constants and so on. Just to take one example from her presentation, this matter-antimatter, very, very slight imbalance. But if it weren't, if there were absolute symmetry there, then there'd be no stars, planets, life, and so on. So this question as to why it is so does seem to me to crop up all the time as this amazing, remarkable story is told, as well as the points that Katarina was making at the very end about the orderly and order structure and so on. Why does mathematics might be a product of the human mind or whatever? It might inhabit some Platonic realm of its own, but how come mathematics applies to the universe at all and so on, and we can understand all sorts of ways in which these more metaphysical questions arise.
What would you say, Bengt?
I would say that, to me, physics is most interesting when it is bordering metaphysics. I think all of us being scientists are not very interested in knowledge. Knowledge is for others. But for us, I think the unknown is the interesting area of exploration. And the unknown is outside physics, it's in metaphysics. What we try to do is, in a way, naturalize or explain the world, the metaphysical world, and make physics of it. And in making physics in a wide sense, then, we are strict in requiring certain principles which may be in conflict with the religion. One is reproducibility. So we are only interested in observations, in principle, observations, facts, whatever, that can be seen by all of us if we describe what we did. If we describe how we carried out an experiment, you are supposed, in principle, to be able to carry out that experiment, although it may be difficult to discern, and get the same result. And if you don't, this is not science, in principle. And there's another principle of this character, and that is the consistency. We want our explanations, our theories, our models, to be logically connected. So, if you advocate that your metaphysics or your religion should absolutely contain a number of paradoxes, then we may be in problem. And the scientific idea is to avoid paradoxes. We can't totally, but we try to. And we discuss them a lot when we come across them. The third principle then, leading from this, perhaps by experience, leading from these other two principles, is the predictability. We want our science to predict new things, and not only predict expected results, but if possible predict quite unexpected, unknown, new phenomena which we could never dream of. That's a measure of success of science, if you can predict such things. And go out, for instance, look for black holes, and find them. So these are kind of criteria. And then, as regards this question then, how does this border to, or get in touch with, or get in conflict with religion? To me, this is very much a question then of what you mean by religion. Is your religion a private issue? Does it contain general principles which everyone can see? Or is your religion free of paradoxes? Or is your religion able to make unexpected predictions? If your answer is yes to these questions, I can't see any difference between your religion and science.
Thank you. And Katarina, what would you say?
I will maybe try to attack the question from the point of view more of religion. I have a feeling that you spoke more from the point of view of science, physics. I will try to start from religion, and I think it's very important to stress, especially today, that science is actually relevant to religion, because that link is not as obvious as earlier, where you had a stronger tradition for natural theology, and that's really what's gone. So, and it's not only so to claim that science is relevant for religion, an understanding of nature is relevant for your religion is crucial, I think, today. But because I think what we may see is a decoupling of religion and reason, rationality. Religion is becoming more and more defined as a private matter, and so subjective and private matter. And I think that this decoupling of faith, theology, religion from reason is also very dangerous, and I think Pope Benedict has spoken very clearly about the dangers of this, cutting off religion from the rationality. You lose the common ground of dialogue, and in the same go you lose a common ground for ethics, and your religion becomes very vulnerable for fanatism. But so this is a very different. So I'm now pulling this very far, but I think a very important meeting point, or like an anchor of religion is also this link to science, knowledge about nature, and this, So, and I think with this, it's also a question of the credibility of a religion, if it can relate to current knowledge and somehow integrate or relate to it in a reasonable way. I think it's an important question of credibility, because it's a kind of a maybe escape to say it's difficult. No, but religion is about something subjective. Okay. So.
Yeah, thank you. But rationality is, I guess you would agree, a more broad concept than science. So maybe there are still different ways of being rational. I mean, you can be rational also if you do historical research and so on. But is there even a kind of overlapping of the questions, or is it at the end still different questions that are being put in physics and in theology?
I think clearly the day-to-day sort of working of a physicist in a laboratory is looking at very particular examples and looking at the Higgs boson and so on, firing all these particles into each other and all of that. My feeling is that day to day the physicist isn't thinking about the big metaphysical questions, but doing the nitty-gritty job. And so, but on the other hand, I think theologians really are thinking, that's their purpose, is to think the big questions pretty much all the time. That's what theology is about. Why are we here, and what's the purpose and meaning of life, and how do we relate to God? How does God relate to us, and all of that? Where are we going? Is there a destiny beyond death? I mean, these are questions that take us way beyond the kinds of things that physicists are doing, as it were, day by day in the laboratory, even though at some level, some of those answers that they're finding do feed back into the bigger questions.
I would like to say that I think the popular presentation of this is not up to what I experience as a scientist. It's common to say that a scientist, he says how nature behaves, but not why nature behaves the way it does, and that's wrong. I think very much of our questions driving science, in particular at the unknown, the frontier, so-called, is the why question. To one example from my own present work, I'm very interested in why the sun has a chemical composition somewhat different from all the so-called solar-type stars. So the solar-type stars are there in the parameter space. The sun is there, almost alone. Why is the sun different? That's a good why question, and we don't know the reason. So I try to ponder upon what is the difference between that why and questions like, why are we here at all? Or why did this happen to me, this unfortunate thing which changed my life, or this fortunate thing which changed my life? Those existential why questions, are they really so different from the questions I raise and other scientists raise in their daily work? I'm not sure. What happens, of course, when you have this kind of why question in a science problem is that you try to answer it using the world around it. I mean, the surrounding world. You look in the papers, you go to measurements somewhat different from the ones you have done. You try to respond to the question within your standard framework. But I think that's also what you do if you come to a, say, crisis in life. You maybe not find this standard framework suitable for answering the question, but you start there. So I'm not sure I see strictly this difference. There are maybe other differences in science and religion which we hinted at before and which we can explore, but I don't think the main difference is the questions asked.
You asked explicitly about overlap, and I think that maybe go back to a picture which was used in your lecture about different levels. So maybe I think there may be a kind of overlap, but it doesn't mean that they sort of step on each other's toes, but maybe there is an overlap, but on different levels. And again, these questions, bordering questions, metaphysical ones, and that science is really relevant for science. For me, it's an important question to have a religion or a faith which somehow manages to relate in a reasonable way to the knowledge of not only natural sciences but also other sciences, and that what sort of makes the difference? Why is it more reasonable? Or why is it more religiously satisfying, or in a way, to believe in a theistic God and a God and a Christian God, compared to the flying spaghetti monster? Yeah. So, but it's a little bit on that level. Overlap in the sense, if we can manage what kind of religious view or view of understanding of science allows you to make as complete picture of the reality as possible. So it's, I think there are concrete notions for this kind of view, this cumulative argument, case of best explanation. But what gives the most coherent view of reality, of a reality where there is also a God?
May I add to this also that I once made a rather systematic study between the chapters on God written by the 20th century physicists. There are many such essays, you know. Often the last essay in a small volume is about God. And I tried to classify the kind of religions that these exposed, and I found all sorts of religions, from vitalism to Buddhism, Taoism to Christian faith, and rather often mystic Christian faiths. And then I explored these mystics in science, what characterize them, and how are they kind of related to mystics in Christianity and in Christian traditions. And there are clear connections, but there's a difference, and the difference is interesting, I think. Namely that, just as the mystics in religion keep searching and expressing and talking and writing about something which has to be there. They have this vision that there is something, but I think they are convinced that in the end they won't be able to do it. Still, they insist in doing it. You know, it's a very moving tradition, I think, this attempt to explore things which we can never understand. But still, you have to do it. That's how I read, at least some Christian mystics. But when I read the corresponding scientists, they express very much the same, but they have a feeling or express, that, like Einstein is a good example here, that there is the truth that they will find. You see? So the scientist, as a mystic, believes that in the end he will understand it all, and even write down the equations, write the papers, even get the Nobel Prize for it, in this world, which I don't think is I don't think the Christian mystics at all have that convincement. So in some sense it seems that the science mystic tradition is still, what do you say, immanent.
Thank you very much. I would like to go on with a more specific question, and I would like to start with you, Rodney. You have been speaking here about the anthropic principle, or you would like to speak more about fine-tuning, actually. Could you tell a bit about that, and what would be the relevance of that in theological terms?
Yes, the reason I speak about fine-tuning rather than the anthropic principle on the whole is that the anthropic principle comes in various forms, some of which can be somewhat misleading the way it's expressed. I mean, there's the weak anthropic principle, which tells us that we can only measure the constant values of constants and so on that are necessary for our own existence, which is kind of like a tautology, but sometimes it's taken almost to point to a multiverse kind of explanation. Well, we're in a region or a universe out of many universes in which that's the case. Then there's the strong anthropic principle, which says, well, in the way it's put by Barrow and Tipler, the universe must exist, it must come into existence. So the conditions must be right for life to come into existence, and that's sort of connected, I think, with the kind of John Wheeler idea that of the participatory anthropic principle. In some sense, we bring the universe into existence by making measurements. That's related to quantum theory, but sounds quite bizarre, I think, probably to many of us. Anyway, but what I think the actual values of the constants, taking the values they do, which do seem necessary for us to exist, for intelligent life to exist, I think that does feed into theology. It raises a question, well, why is that so? Why do they take those values? Now, there may be explanations in terms of more fundamental laws which predict those values. But the why question doesn't go away, because it just gets shifted up to the level of, well, why are those the laws that apply to the universe? That give just the right values for the constant such that, 13.8 billion years along the line, here we are. So I think they do raise this existential question, this question which theology actually has a very satisfying answer for. Well, God had purposes and intentions to bring about creatures within the universe who had the capacity to relate to him, who had a moral sense, rationality, and so on. I think it does, it does, point to or at least raise that question. I mean, one can go in different directions, perhaps explore other answers, multiverses, whatever it might be. But there is perhaps the opportunity, if you like, for a revised, new form of design argument in the light of all of this, rather different from the sort of William Paley argument, but nevertheless, a new form of design argument that is presented to us. And just to add, where did this anthropic principle all come from? It didn't come from theologians, it came from cosmologists, and at that, atheist cosmologists. Brandon Carter was the first person to come up with this idea. He's an atheist. The next big paper after his was Bernard Carr and Martin Rees. Well, Martin Rees is an atheist. So, serendipitous. Fred Hoyle made the discovery about the carbon resonance, which is a archetypal, if you like, fine-tuning, and was moved to talk about a super-intellect behind the universe. I mean, again, an atheist, but by his science. And a lot of scientists with no religious axe to grind are really impressed by this. I mean, we talked about Paul Davis in the last few days. John Barrow is a Christian. But this is a live topic in cosmology. Unlike, for example, the sort of design argument we're getting out of the Discovery Institute in Seattle, in Intelligent Design, capital I, capital D. This is a live topic of debate in cosmology, amongst professional cosmologists.
Well, what would you both say to this? Bengt, would you like to begin? Or Katarina?
Question maybe. But I'm not sure if it's a relevant question or correct to phrase it in this way, but I have a little bit feeling, or also when it comes to entropic principle, there seems to me to be or is there some, how do you relate on one hand explanation and on the other hand interpretation? Something that,
Explanation and
something
interpretation.
opposite. I mean, I think the weak entropic principle with this formula, well, more like a boundary condition with, I'm not sure if it's correct, but saying to cosmologists, well, it's fine, play with whatever theories you like, but as long as it leads to carbon-based life, it's just like a boundary condition for I mean, so it's just like a limitation. Not all the models are equally correct. I mean, they have to end up with certain...
Yeah.
Because we are here and we are the solution.
Exactly. It's like a tautology, if you like, in that sense. It has to be. But nevertheless, it's useful.
But again, so what is the relation or between these as explanation or interpretation? I feel that one could accuse, well, but this is not an explanation, it's an interpretation. We know the solution in a way.
Do you want to answer?
What do you want to answer?
I can leave you thinking of it and see if you have an answer after. I think that the entropic principle, you know, I've been working rather much on the existence of carbon in our universe, and that is related very much to Fred Hoyle's early discovery. And actually, I think this paper by Fred Hoyle in the early 1950s was the most dramatic achievement of the entropic principle reasoning, where he could predict the existence of certain resonances or certain levels in the carbon nucleus from just the existence of carbon in the universe. Good enough, it was there when they searched for it. So that was impressive. But I'm not so impressed with a number of similar achievements of this principle. I would actually say it hasn't been very useful. There are a few other things, and one thing which is debated a lot is whether the entropic principle really contributed to the understanding of the discovery of the so-called dark energy. There are some people advocating that, but it depends on how you interpret a certain paper by Stephen Weinberg and collaborators. My general feeling is that the entropic principle is interesting as an explanation why the laws of nature or the constants of nature are so well fitted for us. But it hasn't really been very productive, unfortunately. And here we can compare with another such principle, which have been used a lot in biology. And that is, why is, etc. Why are the fins of the shark like this or whatever? And then people say, okay, but it works better if they are like this. They explore the hydrodynamics of the swimming of sharks and say, okay, they are optimal. Okay. This kind of why has worked quite well in biology. But of course, the underlying understanding is that there has been a selection Darwinian mechanism behind this optimization. We don't have such a principle in cosmology. I mean, it would be, I think many of us would love such a theory for what happened in the early universe when the laws of nature really found out of how to be from a chaos. You know. I think we have in the back of our heads since Hesiod's times this idea that we would like to understand nature as coming from a totally unspecified situation, and then the laws of nature in some way develop to what they are today. But we don't have at all that kind of theory. And so the only thing we have, if we want to give a kind of rational explanation, why is it so well fitted to us, is either the designer hypothesis or the idea about very, very many universes with different laws of nature, where we happen to be in the one habitable, because where would we else be? Okay? And then, of course, there is a philosophical problem here. We have a working hypothesis. We can, as a hypothesis, say it is probably optimal for us. And that leads to a few achievements in cosmology, like understanding of carbon. Okay? But was it really the intention behind that it should be like that? Is it really designed? Well, we can't say. But if we don't say so, we have to advocate an enormous ensemble of universes with different laws of nature, which we don't see. So it's a colossal metaphysical construction, outside physics, that is, outside observable physics. A colossal such construction that we have to advocate if we don't go for the design argument. And I think this is a problem. Physicists divide between these two attitudes, and many of them retire into a situation when they say, this is hardly physics, we can't answer these questions. They are beyond our capability or our legacy to try to answer. But others are bolder. Some people say the huge ensemble of universes must exist, and there are some other arguments we can talk about why they could exist. We don't see them yet. And the other class say maybe it's designed.
I would like to two questions come in my mind when I hear this. The one is, what does this multi-universe theory, how does it, what the effect has it on this fine-tuning argument in a theological sense? And what about Occam's razor? Where does it come in here?
Well, yes, I think you've crystallized it really rather well, saying that there are essentially these two options. So basically, if you are an atheist, you're pretty much forced into this multiverse explanation, which is from a scientific, and you're trying to be scientific, and yet in reality you're being utterly and totally speculative. And postulating universes that I think pretty much in principle can't be observed because signals from other universes can't ever reach us. So and in terms of Occam's razor, well, you know, this is a principle that says we should do with the least entities necessary, least kinds of entities, least entities necessary in order to explain the data at hand. If we've got competing explanations. So the multiverse hypothesis seems anti-Occamite in principle. And in any case, you still, if you go this multiverse route, you still have to choose which multiverse you invoke. Now, it might be the M theory, string theory version of the multiverse. Well, we know that if that's instantiated, there'll be a universe which gives rise to life, to this universe. But why is it that particular multiverse that is indeed instantiated and not one based on some other mathematical principles or no mathematical principles at all? So this particular why question, it seems to me, never quite goes away. I mean, it always gets just shifted up a little.
So this is more a question from astrophysics. Does it mean that the idea of one theory is sort of given up as the dream of Einstein, that there must be some underlying theory and these kind of multiverses are more trying to avoid or hide our ignorance, in the same way as he didn't accept the probabilistic interpretation of quantum mechanics. He still thought that at some point we would understand. But is that route sort of given up, or yeah?
Just briefly on that.
Yes, I think there's a temptation, as I think I was saying the other day, to give up on what you might call normal science, to look for the grand unified theory that actually does do the calculations and produce real numbers and measurements in the lab, to say, well, give up on that and say, well, actually, all possible numbers are instantiated in some universe or other.
Yes, I think that there are quite different attitudes here among different colleagues here. One, which is represented here in Uppsala, by the way, by Ulf Danielsson, is that this ensemble of universes follows, perhaps, he argues, probably, from superstring theory. And there, through spontaneous symmetry breaking, you get all sorts of laws of nature, or at least all sorts of constants of nature. So the situation for him is roughly imagine in the old days, there was this idea that the distances between the planets in the planetary system follow some kind of very general principle. Kepler worked along those lines. He never found that principle. He found other very beautiful laws, but not that. Nowadays, we know that planetary systems may have any sorts of design. Our planetary system is one representation of much more fundamental principles, with certain things which aren't laws of nature. The distance from the Earth to the Sun is not a law. The reason why the distance from the Earth from the Sun is as it is because we live here. Because we need enough of sunshine, but not too much. And so, there's nothing holy. That's not even perhaps a design argument behind. It's just that where we could be born. Okay. But there are other planetary systems all over. And this situation then is, according to this school, resembling the situation with a meta-theory, which some people think we are approaching, and that meta-theory gives us all sorts of laws of nature, or at least constants of nature. So that's one attitude. You have other extremes. An interesting extreme for Swedes is Max Tegmark, and there's a newspaper article about him today in Dagens Nyheter, where you can see that he advocates a beautiful and, in my eyes, very mystic theory. But he really goes for it. And that is that all non-trivial mathematical system is represented in the observable world, or in the world at least, by a universe. So you have an enormous amount of universes, and the characteristic feature of all universes is that they are rational in a mathematical sense. Okay? That gives room for enormous, very different worlds from the ones we know. But it's beautiful, and it's really related to this issue you discussed earlier, I understand, namely the relation between our mathematical minds on one hand and the universe. Maybe all ideas we can find out of in our brains that are mathematically structured are actually up there, according to Max Tegmark. So you see, there are wide areas of speculation here, quite different attitudes among physicists to what we could have. But it might be, I think we should think in these terms too, it might be that, imagine that the Earth's atmosphere was always covered by clouds. And we would be living here on Earth, and we would ask ourselves, how comes that we have a temperature which is suitable for us? That is, water is not frozen all the year, so life can form, but it's not in gaseous form. It's not above 100 Celsius. How comes, would people say? And some speculative mind would say that maybe there are other worlds out there with very hot or very cool temperatures. But others would say, no, we don't see any of that, because double clouds. We don't see any of that doesn't exist. That's just metaphysics. And then, a beautiful day, the sky would become clear. And people would see all these other worlds. Maybe we are in that kind of situation, but we don't see yet.
First, Katarina.
But maybe it doesn't mean I will argument against, but it doesn't mean. But isn't there a principal difference? Because in principle, you can look beyond the clouds, while with multiverses, are there any possibilities to actually observe them or derive some observable, some predictions which could indicate anything in principle? Isn't there? Yes.
In principle, those people living in the cloudless skies would say it's in principle impossible to see anything. So I think that's one thing I would like to preach as a scientist. Never say never. Never say never. If you think of what science has accomplished during this century or the previous century, people, in the end of the 19th century would say, no, never. And we do it now. So, sorry.
Yeah, but that's one of the arguments, or
yes.
We would really like to see something we could test in our experiments.
Yes. As long as we can't see it, we have no strong reasons to believe it. It's just theory or just speculation. Yes.
But at the same time, I very much see that one of the reasons why we go on with these speculations and why we even manage to convince our authorities or research councils to give us money is that the theories have exactly gone through so many confirmations and these nevers which have been broken. So I very much see that and that's why it's meaningful to speculate or work theoretically on this issue, but still it's from an experimental point of view it's a bit disappointing. It's really far beyond the reach of what we can test in experiments. That's unfortunate. That's quite an unfortunate situation. We would love to see some of these. Yeah.
I would like to. I think there are two questions arising here. First, what is science? How strong is the demand for empirical, some kind of at least relation to something empirical? Where is there a limit for reasonable speculation or not? That's my first question. The second is, even if you go for the multiverse theory or some kind of, does it really solve the question that is relevant for theology, which seems to me to be much more Leibniz question? And I don't think that the multiverse theory solves it.
Sure. On that last point, certainly, there's still the question: why is there a multiverse rather than no universe or nothing at all? I mean, that question will always be there, and none of this speculation will reach it. But a couple of points in relation to what's just been said, if I may. It looks like with the main multiverse options that are on the table at the moment, that even in principle we won't ever be able to observe anything from another universe. If the background space is expanding at faster than the speed of light, and you've got universes, billions upon billions upon billions, 10 to the 150 or something, times further away than the furthest reaches of our present universe, and expanding away at faster than the speed of light, no signal from there will ever reach here, okay? So we will never be able to observe such a thing. Quantum universes branching off according to Hugh Everett's theory. These are in principle unobservable at least as far as I understand it. When you then move to the sort of Max Tegmark picture of any mathematical structure having physical existence, that's yet, an even further remove away from any possibility of verification, seems to me. And if I just to add to something you said a moment ago, which struck me in terms of the way anthropic reasoning goes. And I suppose Hoyle was using this really too as well. Because we are here, at the distance of the planet from the sun is so and so. The distance of the planet from the sun is that because we are here. That's kind of a reversal of normal cause and effect. We're here because there happens to be a planet at the right kind of distance, if you like. But the fact that we're here is in some sense an explanation of why that's so. So that, it's certainly related. Those things are related. The universe throws up planets that are right kind of distance and sort of Goldilocks zone sort of planets.
I think when I look, the older I get, the more I regard science as a human endeavor. Science is an ongoing, serious discussion following certain rules among humans. And it tells a lot about how humans are and how society is. Anyhow, from that point of view, it's interesting to see the recent development. We have all been fascinated by the discovery of polarization patterns in the cosmic microwave background, and they were rapidly interpreted as the result of gravity waves in the very early universe. So suddenly we had a kind of window, or at least indirect still, but signals from the very, very early phases. Now, it happened to be so that André Linde, a famous physicist, had predicted these kind of things as a result of a theory which actually was a kind of rather everyday multi-universe model. And so people said, okay, they exist. And that's not true in the sense that these patterns seen in the cosmic microwave background don't at all lead to a necessary conclusion that we have multiverses, a multiverse. But, on the other hand, if you look at the history behind, it was part of this framework of thinking that led to the prediction of these patterns, that led to the search for them, and they were there, you see. So one could say, strictly speaking, logically, it's not a proof of the existence of them. But still it gives an indication that, yes, the idea worked for a while at least. It produced something. And I think this will be the kind of criteria that people will apply for the years to come as regards the value of this idea of a multiverse. That is, if the multiverse idea, or ideas, or theories, if you wish, if they produce some more possible observations, and people go out and see the predicted pattern, then there'll be a tendency to believe more in these things. It doesn't prove that they are there, but it gives, it shows that scientists are rather practical minds. It shows that, yes, here we can use something, we can find something from this kind of principle. And there, if you compare that to the design argument, I mean the idea of a creator, then you have a problem as a scientist. It may be right, but the problem is, what can I then deduce from that? I mean, is there new science to be built on this idea that a super creative force made it up all to fit us? If you can make more science from that, yes, then it will attract scientists. But if you can't really say anything, if the boundary conditions are fixed, and you can't make more science of that, I'm afraid that it will be regarded as a dead end from a scientific point of view. Which doesn't mean that it's not correct, but it means that it is a not very productive idea. You see? What do you say about that?
Yeah, that's a good point. But I think what the idea that the designer does for science is, even if we go back to the sort of period of the scientific revolution, a lot of the motivation was theological. to discover what God's universe is like, and we know what it's like in the sense that it's going to be ordered and structured and comprehensible to us and so on theological grounds. So a designer, we would expect to create a universe that has a rationality, and so there will be reasons why, it doesn't look as though, say, I don't know, the cosmological constant, it has to be low for us to exist, but, why is it as low as it is, or this sort of thing. A theological motivation would be to look for a real reason that it's what it is, whereas the tendency, if you're a multiverse theorist, is to explain more things on the basis, we just happen to be in one of those universes which has that particular characteristic. So I think theology does give you motivations to actually seek answers within what one might call normal science.
Well, that's what we try to do, at least. No, because we are on a much lower level in this, for sure, looking for supersymmetry, trying to, but that again, I think we sort of work from below. Very much the ideas of multiverses is a little bit from starting from the very top, and we trying to climb up the ladder, small steps, finding particles, and confirming theories. You mentioned superstrings and supersymmetry as a very important step towards these kind of theories, so I very much believe that. Because we believe in this order, and we have seen so many impressive confirmations of this interaction between theory, the tremendous imagination of theoreticians, and for sure quite a lot of imagination and creativity from the point of view of experimentalists developing incredible technologies to confirm these things, but still, it's this question of normal science also that our daily work is to slowly climb this ladder of knowledge in a way, confirm things, but one interesting thing is that you ask what is science, what we do mostly at the moment is not to to exclude models. When we speak of especially supersymmetry, there are many models on the table, and what we do now is more and more to exclude and see if we can narrow the range and pin down if these ideas are realized in nature, what are the parameters? It was the same with the Higgs mass. It was excluded, and the range narrowed down, and then finally it was found within this narrow range. So this is also how, and maybe that's also how things will continue. This, for sure, with the discovery of Higgs particle and pinning down the mass of it, for quite many theories or models, not theories, maybe models that were excluded, and the supersymmetry is discovered, that quite many will be sort of excluded again, and then maybe that's how we will. Can we sort of approach somehow these more speculative ideas in this way?
I think this illustrates something which I think is a fundamental property of our universe, namely that it is very special. It's really very special. And that brings me to a quote which I think of rather often, namely Einstein's. He has many quotes. And that is this: what really interests me if God had any choice when he made the world. Maybe he had to make this special universe. I feel pity for that. I think it can't be good to be a creator, having all these possibilities, and then be forced to do exactly this in order to get company. And so I feel some sympathy for the idea that, oh no, let's liberate him or her. She had all possibilities, and they are there. We don't see them, but isn't that, from a theological point of view, much more satisfactory?
Indeed, some theologians certainly think so, and some Christians who are
Gustafsson did, actually, isn't it? Gustafsson.
Ah, well, indeed, yes. Yeah. So we're talking about the Cardinal Nicholas of Cusa in the 1400s, early 15th century, I think, who first, I think he may be the first speculator about multiverses, I don't know. I mean, it's rather interesting that, well, if you go back to the Decree of Paris in the 13th century, I think one of the things that the Bishop of Paris said was that God can create as many universes as he liked, because there was seemed to be a certain limit on what people were saying God could do. So, yeah, and certainly today there are theologians who are quite happy with lots of universes. I suppose one trouble with them is that the vast majority of these universes are completely dead and boring and have nothing whatsoever of interest in them. So you wonder what God's interest might be. I don't know.
Can't you say he had to continue? I mean,
well, you're saying God had to again. You see.
Went on until he had to.
Kind of gigantic experiment, and he got one that did the right thing, so to speak. I don't know. Possibility.
I have a question that I would like to put to you. Last year, Lawrence Krauss was here, and you, Bengt, you met him and discussed in public with him. And he published a book also, The Universe Out of Nothing, and I read it, and I'm sure I missed a lot there. I didn't understand, but one, I was a bit suspicious at the end that he didn't really give what he promised, a universe out of nothing, because the nothing that he tries to describe there seems to be full of. So I have the impression that when physics talks about nothing, it contains a lot. And when theologians speak about nothing, there is actually nothing. Is this a correct observation, and why is it so? Can't we agree that nothing is nothing?
I think this Lawrence Krauss book is it's a nice popularization of something which is rather common ground in science now. But to this he has added some very sweeping arguments which I think are not valid. I mean, they are not proven to be right, and he presents them such that you get the impression that this must be the truth. And this is actually accentuated by Richard Dawkins, who writes a preface, or I think in the end of the book he writes comments on this, that now we have a kind of Darwinistic killing of God. Also in physics, which is so nice to see. I think that's a misunderstanding of what it is about. But what it is about is, as you know, that vacuum in the lab, if you try to make it, you find it filled, over-flooded with quantum fluctuations, which lead to particles and antiparticles that annihilate before you can see them, but you can indirectly show their existence by observing effects on atoms and other systems. So this happens all the time, and it's a consequence of the Heisenberg uncertainty relations. And so what it actually means is that you take from nothing, you form matter and antimatter, and if you leave back the energy, because you need energy to do this. If you leave back the energy within a very short time span, you are allowed to do this, because energy and time are not well defined enough. And it's a consequence then of quantum mechanics. And that in turn, well, it is corresponding to, I mean, you rush into, you rob the bank, you take the money, invest it, and leave it back to the bank, the sum you robbed, before they notice it, you see. It's something, well, it's done, I think, in the stock market today, so it works. Yes, but my point is that this has been then used also to introduce the very first moment of the universe. So this is happening in the universe, and it was probably, or most probably, the factor that led to the formation of the largest structures we know, the clusters of galaxies. In fact, you can interpret the existence of our largest structures as the result of early universe quantum fluctuations, which are about the smallest and most trivial structures we know of. So that's a grand idea. All these fantastic structures which we see out there, where we are a small part of one of them, all those are the result of the least, most innocent events that occur in front of our eyes in the lab, and also in the early universe. But then this is brought to the very beginning of the universe by some people, including Lawrence Krauss, saying that the whole universe may be the result of such a quantum fluctuation. So there wasn't anything, and in this anything there was a quantum fluctuation, and that's the Big Bang in the end. And question is whether this works, and we don't know, but in principle it's an attractive idea from a scientist's point of view. Maybe it's all right. And you say it's impossible because there's so much energy needed for the driving the universe. That's not true. That's depending on how you define your energy 0 point. But there's lots of gravitational energy which is negative to begin with, and which compensates the positive energy of matter, and radiation. And so maybe you don't need any energy to make a universe. You can make it in your kitchen. There's a good paper by Alan Guth. How can we make a universe in the kitchen? It says something about the interest in astronomy among astronomers. Anyhow, I think that this idea of the universe as brought from a quantum fluctuation is natural, but it's not supported. There's no clear evidence for it. We don't know whether it works. But please, if you are Christians or believe in creation, don't attach your idea about creation to the very first moment. It may be very trivial.
But I will just, this is out of my ignorance of theology more, and I'm also not dealing with cosmology. But you said that why limiting God? Why couldn't He create all this? But on the other hand, these classical ideas of features of God, of omniscience, of being perfect. Why shouldn't God create only one universe? Is it like, because it sounds a little bit, well, let's try a couple of times and see when we succeed, or this selection mechanism. But why not one universe? Is it really a limitation of God? Or is it more maybe an expression of God being perfect, omniscient?
I just want to add that all this quantum vacuum stuff is perfectly well and fine, but it's not creation out of nothing. That's the thing. And this is the hype that it goes with that book. Okay, fine.
Yes, I mean one thing which is required when it happens is the existence of quantum mechanics. I mean, it's built on some principles which are not taken, well, in Doris' book they are taken out of the air. But then, concerning this question of God, I mean, you have these fantastic pictures of God from late medieval times where he stands with the earth in front of him and the skies around the earth, and then he has this big compass, passare in Swedish, which is a signature of the builder of cathedrals. And that's of course a very worthy symbol, I think. I mean, in those days, you take here in Uppsala, all houses being small and rather not nasty, and then this fantastic cathedral on top of the hill there. That's really something. Of course, they impressed people a lot, and duly so. They still impress us. Anyhow, if you think of the cathedral as something created on drawings by an architect in the beginning, then you have this picture of God, the fantastic architect. But if you read about the history of making cathedrals, they started and it fall apart. And they started again and again through centuries. Very, very admirable, I think. That's a real creation. In the end, it stood there after some 300 years. And not only because of lack of financing, but also because of that was not so expensive. So this is very personal. It's totally religious speculation, but I would like to defend a picture of their creator as an experimentalist. Maybe it's because I'm a theorist. I'm very much more impressed by experimentalists.
I would like to move on to a question about, we mentioned it at the beginning, the relationship between natural science and mathematics. This relationship is very tight. But how does it come that you can use mathematics on nature and you seem to go into a Platonic worldview very rapidly then. But science to me seems to be footed on the empirical. So what is the relation between these aspects of science, and why, or am I wrong, why aren't scientists more bothered about this problem?
Just to say one thing about that, there was a very interesting paper quite a number of years ago now by Eugene Wigner entitled The Unreasonable Effectiveness of Mathematics in Science, or I think it was called. It is, I think, a truly astonishing thing that the physical universe somehow maps onto the kind of mathematics that we can understand. I think many mathematicians think that mathematical theorems are up there in a kind of Platonic world of ideas or forms. But it's truly, I think, a remarkable thing that the kind of mathematics that we can understand, that we come up with, and then go and find that physics, applies to group theory and so on. This work of Abel and people of that kind. We go and we find that the world, the physical world, can be understood in terms of this mathematics, and I think that is truly, truly astonishing. Was it even Galileo who said that God is a great mathematician? So I think this is a truly amazing feature about the world, and again, I think it does speak of God, the great, the God who's behind it.
I think this is not understood, and it's probably deep, and it's very interesting. It's I think, one of the most interesting problems we have discussed today. I think many of us who are in theoretical physics ponder upon this, but we don't have clear answers. We have to respect this problem as a deep and interesting one. personally, I'm most impressed with the fact that you can use mathematics and you can build your mathematical models from your everyday experiments, and then you can extrapolate. You can use some mathematics to predict quite new phenomena which you have never dreamt of, which are absurd, and still they are there when you search for them. So mathematics is so powerful. That's what Wigner talks about, this extreme efficiency of mathematics for these purposes. And the answers, there are a number of answers people have tried to give. One is that we are so selective, that we take the beautiful, like Newton said in his kind of humble, or I wouldn't say he wasn't humble at all, but he says that he picked the beautiful stones on the shore, you know, while the full ocean was out there. I think that's not so any longer. We have really, the stones we have picked are covering quite a lot, in particular in the universe. So I would say it's not that, even though we have to admit there are a number of phenomena on Earth, like weather, which are just extremely complex and almost difficult to describe with any beautiful mathematics, I mean. So it's chaos. Yeah, chaos is anyhow. Another answer is to say that we carry in our, I think Kepler was on this line, and Jung, we carry in our head some mathematical patterns, and we project, in a sense, what we have in here onto nature, or we correspond in a deep way with nature. That's a trivial version of this, which you find sometimes. Biologists I know come with it. I think it's totally wrong. They say that we are, after all, born in the nature. We are children of nature, and so we have these patterns of nature in our heads. Yeah, that's good enough, but it doesn't explain how we can predict phenomena like black holes and whatever. We have never been close to the interior of matter. So that idea is not so. Maybe you can say, which I think is also right, that as Martin Rees has, that whatever is the reason, it's very clear that nature is woven in one big, what do you say, sheet. I mean, you find in all scales similar pattern repeating. You find a kind of aesthetics of nature which is really going through it all, often creating new structures, even absurd structures, but they are essentially showing the uniformity of the world. And I think that is a fundamental observation, but I don't think it explains why mathematics works so well. So, after all these words, sorry for them, we don't understand it.
I'm not sure if that's true. I very much agree. And well, when we do experiments, we depend very much on models. But exactly this, it's not only mathematics and laws, but exactly models. And it's maybe more a question, but I don't, people like, I think like John Polkinghorne, he has some very nice explanations of parallels between theology and science. Exactly this, how much we depend on models, explanations, but at the same time that they really refer to something out there, something real. So this idea of realism, or critical realism, which I think is also quite interesting. I won't do any attempt to explain it, his ideas, but I think maybe that could be related also to this puzzle of mathematics, and that it's actually corresponds to something real, and this interesting parallel to theology, that our understanding, that this capacity for God, our theological capacity to also grasp some reality of God. Just to draw a little bit further on your, if it's correct. But, yeah.
I guess there is the question of the intelligibility of reality. how does it come that reality is intelligible? It seems to be, at least it works very often. So, this question, of course, is related to that. Assuming that mathematics is something that comes from human brain, is a product of us, if you assume that, still it seems to work. And so reality seems to be intelligible for us. It's not, we take it for granted in everyday life, but you can put the question, how does it come? We agreed at the beginning that I will give you some time at the end for some kind of concluding reflection or so, but I will do so with two questions. But you don't need to answer them if you don't want. But you can go into them if you want. I think it was 1905 or so, around that time, the Nobel Prize winner in physics, he explained that we have now understood basically everything in physics. There is nothing of real importance to be detected anymore. But the story went another way, and not so long ago, you started to talk about dark energy, and that we have really grasped very little of what there is in the physical universe. Is there more to be found? or are we actually very much in the beginning of understanding what we are trying to understand in physics? So will physics go on like this to develop in a very unpredictable way? And and the second question related to that, will future physics or future cosmology have relevance for our religious beliefs? These are two big questions, but you can go into them if you want or not. You can choose who begins.
I'll have a go. I think the first is a very interesting question. And yeah, the idea was that everything was sewn up. All we had to do was measure the values of these physical constants to more and more decimal places. And that was proved just so wrong. And I think there's an element of hubris about today with these notions of a theory of everything that is just round the corner, or even maybe we've got it with M theory. You know, I'm afraid if you read Hawking's book, The Grand Design, you kind of think, we're pretty much there. And that just is so counter to the history of physics. And so I think there is a lot more to be found. We might find supersymmetry at the LHC. It might indicate string theory is the right theory. It might indicate some other theory is right. Who knows? But it's exciting. Whichever way it goes, it's exciting. And I tend to think that God's creation is just so inexhaustibly rich that we'll go on and on as we have done by answering some questions, only to find that for each question we answer, there may be 10 more out there that are then raised. We now know what 5% of the universe is made of. At the beginning of the 20th century, we thought we knew everything. And to me, well, maybe that's a prediction, I don't know, that we will go on and on finding more things about the universe. And that, to me, does say something about God and about, the bountiful and amazing sort of God that has created the universe. Maybe I'll stop at that point.
I can
maybe say something more from experimental point of view, and then as a theoretician you can draw a bigger picture. So is everything found? Well, at CERN, as I was in Europe, there are a couple of things we are joking with, so there are known unknowns, and so the Higgs particle was a typical known unknown. So it was, for years, it was said to be the particle we knew everything about, except whether it existed. So now, so these are known unknowns, and I think supersymmetry is a little bit known unknown, but still, then there are these unknown unknowns, which we also very much believe in and are open for. So I think that's where we stand today from the experimental point of view. One thing is doing experiments, but also this very important input from astrophysics. This link between fundamental physics combined with new results, observations from astrophysics. That's absolutely fundamental. I would also add another thing, which we have been talking about mathematics, theory. But one more factor is coming into the game more and more, and that's computing. We have nowadays very powerful computers which allow us also to develop simulations, calculations in a whole new range. So there's definitely a future for fundamental science, not to mention all the applications which we develop as we go along in fundamental science, because it's very often questioned why spending all this money. And at the same time, as we deepen our understanding of nature, as I said in the beginning, I strongly believe that we need to do this difficult work of relating or making clear the relevance of science and knowledge about nature with our religious insights, to keep this link, sort of not to push religion, faith out into the subjective area. I think the question of credibility of our faith depends very much on how we relate to today's knowledge society in many respects.
Do we know it all, or do we soon know it all? My feeling is that these words about hybris or hybris are very relevant also today, not only 100 years ago. And partially I suspect that one reason for us showing this hybris, thanks, is our need of your taxpayers' money. We have so fantastic things, and we soon understand it all if you just give us a chunk of money in addition to build a new telescope or whatever. Accelerator, yeah, I didn't say that. But that's a suspicion. I must say, personally, I'm more interested in the question why we understand anything at all. I think that is really interesting. And I don't think we understand much, but we understand some, and the question is why. And it has to do with these problems we have discussed earlier, why we carry some nature in ourselves, not only the nature in the nearby world, but the grand properties of nature. Why is that? We don't know. Concerning their relation between science and theology, I don't think they are separate. I think they are trying to do similar things, they affect each other, they take opposition against each other, like two kids that grow up, but they are really related. I think that interesting and related to this is this other question, the relation between us, our mind,
and our surroundings, or a relation between the subject and the object. We don't understand that, and we don't understand it even on a very fundamental level. We don't understand the relation between the observer and the observed in physics. And because of this, I think we have lots of things to discover concerning objectivity, subjectivity, concerning our experiences that we can't describe using reproducible methods, but still may have considerable truth. I mean, I'm interested in music, I suppose many of you are, and I'm not able to describe my musical experiences in any really profound way. Still, they are very important, and not only for me, but for many of us. So we have things in common which are not at all easy to describe with science, but certainly science will learn us more about how these things that are not describable still relate to us. So I won't separate the fields, I think they are close.
Thank you very much. That will be the end comment of our panel discussion. I want to thank all three of you for this very interesting and thought-provoking discussion. I think we will go on. I think you are very right on that we will go on to reflect on them. Thank you very much.